All right, so here we go. Rates of change in rational functions. So like I said, I'm going to do example 1, 4, and 5. This is something we have done before. We're just doing it with a different function, although it doesn't make it much harder. You just have to be able to substitute in and know the wording. That's key. That's why I want to do example 1, where it says determine the average rate of change. Those are key words there. Average rate of change. For the function, f of x equals 1 over x plus 6. On the interval, and that's key, because average change, you're going to have an interval from -5 to -3. All right, so it essentially means from -5 to -3. Now, when you're finding the average rate of change, so my AROC, what we can do is we can use the slope formula, all right, where we have our y2, well, actually, I'll go with the on the bottom, our x2, which is -3, minus our x1, which is -5. Now, on the top, you have your y1, which means in the function, or y2, I should say, in the function, we are going to sub in a -3. And your y1, we're going to sub in a -5 into this function here. Now, I've already done that, so I don't want to go through the crazy details because I've already found out that f of -3 is 0.33, 1/3. And I've also found out that f of -5, so when I plug in -5 into my function here, I just get a 1. All right, so I substitute those values in for my average rate of change. And so again, I got 0.33 minus 1. And let's see, what do we got on the bottom here? We got -3, minus signs come together, plus, so it should be a 2 on the bottom. All right, and if I do a little bit of, put these together and then divide by 2, it's going to be negative, that's for sure. And I get -0.34 is our average rate of change. So again, when you're finding the average rate of change, it's just the slope formula. All right, no limits. Limits is when you have an instantaneous velocity and it doesn't say estimate, which we don't have today, which is great because some of you don't like those limits, but you're going to see a whole lot in the calculus. All right, now we get to the estimate part. So I'm going to go to example 4. This nice little biology. All these questions I'm going to do here are actually true. They're all true values or true information. It's always kind of nice to find out stuff outside math, kind of combine the two. That's the best part about advanced functions is you get to kind of learn some stuff as you go along. All right, so example 4. After you eat something that contains sugar, the pH or acidic level in your mouth changes. This can be modeled by the function. Let me write this down here. Here's our function, L of m. So that's function. We've got L as a function of m, which is equal to -20.4 m divided by m squared plus 36. All right. Oh, and don't forget the plus 6.5. All right. Where L is your pH level for those of you who are into chemistry. All right. And m is the number of minutes. All right. So L is pH level. And we have m is in minutes. All right. So I got to know my units because in the end here, I got a little therefore statement. Now, keep going here. Estimate the estimate. So we don't have to use limits. That's what estimate is saying. Every time I put estimate in there, it means you don't have to use limits. All right, so estimate the instantaneous rate of change at 3 minutes. So because we're finding out the instantaneous rate of change, all right, we're again going to use the slope formula, but a little bit different is that we're going to have our L function and our at 3, should put that at m equals 3 minutes. So we're going to have our function, but we're going to have 3 plus a very small value, h, that we're going to sub into that equation, minus our y1, which is just L of 3, putting a 3 into this function, all over h. Now I have to pick an H value, and what I always say is pick an H value into the hundreds, because again, when we did the limits, remember H was that very, very small value that eventually approaches zero, gets very close to zero. Because we're estimating, I'm going to pick an H value of 0.01. So for the instantaneous rate of change, I'm going to, just like I did for the average rate of change, I'm going to plug in 3.01 into that function. I'm also, for a y1, going to plug in a 3 into that function. And again, down below, I have my H value, which I have picked as 1/100th. All right, now, again, substituting in. When I substituted in 3.01 into this equation here, I got, and this is something you'd have to check it on your own, I got down to 3 decimal places, 5.137. All right, and when I plugged in 3, I got in 5.140. All right, so just like I did with average rate of change, it's basically the same thing as average rate of change, only I'm picking the distance between the points, whereas in our first example, it was -3 and 5, so that was the interval. Here we're doing between 3 and 3.01. So essentially 2 points that are very, very, very close together. All right, so now I just substitute in my values. So I have a 5.137, subtract my 5.14, divided by my 0.01, and let's see here, do a little bit of math. And what do we end up with? I got -0.03. So what does that mean, right? Because now we have a situation here where this actually means something. Now on the top, that's what we're talking about our pH levels. And on the bottom, our units are minutes. So what our answer is telling us is, therefore, the instantaneous, I'm going to put IROC, the instantaneous rate of change is decreasing. That's what the negative sign is telling us, decreasing at a rate, because that's what we're finding, a rate of, and again, what's the 0.3? 0.3 pH levels per minute. So at that time when you're eating that food, your pH level is dropping. After 3 minutes, it's dropping 0.3 pH levels per minute. That is what we just found out. Any questions about that at all? All right. So then I'm going to fly over to example 5. Back over to example 5 here. So let's see here. Ooh, little Windex. All right. So if you want to read example 5, again, it's a true example, not made up. Actually true. Some of you in the class know I'm also a physics teacher, so here we go. Example 5. As you get farther from Earth's surface, gravity has less of an effect on you. That's true. For this reason, you actually weigh less at higher altitudes. An astronaut who weighs 85 kilograms can use that function right there, WH, to find their weight in kilograms at height meters in thousands above sea level, above the Earth's surface. Estimate. There we go again, estimate, right? So estimate, we don't have to use limits. The instantaneous rate of change of an astronaut's weight when they are 5,000 meters above sea level. Include the units. All right, so again, I'm going to write my function down here. So I have our weight function, or our weight, which is in terms of, dependent on h, the height. And we have 2 times 85. All right, which I can simplify, and above we have an h plus 2. All right, so we want to estimate it at 5,000 meters. Now, our units here is saying that the height is in thousands. So actually, our h value that we're going to be looking at is 5, because it represents 5,000. All right, So because I'm estimating my rate of change, instantaneous rate of change, I'm going to look at this function. I'm going to have 5 plus h. Oh, that's nasty. So that h, that's height, and that's that little h, the distance between the 2 points. So that's a little different. All right, minus w of 5. So we're going to plug 5 into that function, divided by that little h value again. So let's put that in quotations, different h. And again, I'm going to pick the distance between my points to be 0.01. And so what you need to do is I'm going to have to need, well, here, I'm going to write it down again here. So we're looking at our function. I'm going to plug in a 5.01 because that's the h value I've chosen, 1/100th, pretty small. And then we're going to sub in 5 and divide it by our little h value, which is that 0.01. Now, again, a little bit of math that I've already done. I did plug in 5.01 into my weight function, and I got this person would weigh 24.25. And what are the units there? Kilograms? Kilograms. All right. And then my weight at 5, when I plug that in, I got 24.29. All right. So I'm going to plug those values in. All right. So my instantaneous rate of change, what's my first one there? 24.25 minus 24.29. 0.01 on the bottom. Again, I figure out my number. All right, so I subtract the top, divide by the bottom. And let's see here. I just got a -4. All right, now, what does that mean, right? Because you're always going to have to write a therefore statement. And so, again, the units on the top, our weight was in kilograms. And our bottom, we're looking at our h value, our x value, or I guess it's sort of our x value, is our height. Height in thousands of meters. So what this is telling us is that, therefore, I don't have room to write it, the person's, I guess, I won't write astronaut, the person's weight is changing, or actually I'm going to say not only is it changing, I'm going to throw in the words increasing or decreasing, and again it is decreasing at a rate of 4 kilograms per 1,000 meters of height I guess that's it. We can leave it at that. And so for every 1,000 meters that you go up, your weight is decreasing by 4 kilograms. Until you hit a point, this function only works up until, well, this is the physics aspect, only works to you break through the barrier there, and then you don't weigh anything. You're off in space. But for the first, I think it's the first 5,000. Change when they are 5,000 meters. Yeah. There you go. So it's decreasing. Once you get past 5,000 meters, 5 kilometers, as you keep going up, your weight is decreasing by 4 kilograms for every 1,000 meters that you travel upwards. There we go. So again, instantaneous rate of change. We pick a value, an h value of 1/100th, and then we use our slope formula to make that happen. All right, stop the recording.